Let us talk about this problem. We are given two sorted linked lists. We need to merge them in a sorted way. Also, we need to use the same space that is allocated to current nodes. We do not want to create new space for the merged linked list. Let's see this example. We have this linked list 10, 20, 30 and this linked list 5, 25. Both of them are sorted in increasing order and this is our output linked list. We want to merge them in place. What it means is the same space should be used. So next of 5 should become 10 and next of 20 should become 25 and next of 25 should become 30. That's what we want as a modification into the original linked list. So we do not want to maintain original links. We want to modify these links such that both of them together form a single sorted linked list. Let's see this example. In this example, one linked list is empty. So our output is going to remain as one linked list which is given. Let's now see this example. In this example, we have one linked list with node 10 and the second one with 40 and 50. So what all we want is we want to make this node as next of this. And this is our modified linked list. Now please pause this video and try to write down a function that takes heads of these two linked lists A and B as arguments and it returns head of the modified linked list, head of this linked list that is formed by changing the links. Let's now get an idea of the approach. Let's consider these two linked lists as example. So in this approach, we are going to maintain two pointers or references. The first for first linked list A and B for the second linked list. Now which of these two is going to be head of our resultant linked list? It's the smaller of these two, right? So this is going to be our head of our resultant linked list. So if we call head as head of our resultant linked list, then it's going to be the head. Now how do we proceed further? We have decided this is the head and we want to make these changes. We want to make 5's next as 10. We want to make 10's next as 15. And then we want to make 18's next as 20. And we want to make 30's next as 35 and 35's next as 40. That's what we want. So how do we achieve this result? The idea is to maintain a tail pointer also in our resultant linked list. Because if you have the tail pointer, you can append any node after the tail by just doing tail.next or tail arrow next equal to the node, right? So we maintain a tail pointer also and tail is also initialized as the smaller because right now we have added only one node to the resultant linked list and this is also tail. Now whenever you add a node to the resultant linked list, you move ahead in the linked list from which you have taken the node. So we took the first node of this linked list. So we are going to move ahead in the same linked list and we are going to call it B and we are going to move B here 15. Now the remaining steps are simple. The first steps are extra corner cases because your head and tail would be initially null. So first thing you do is you simply pick the smaller of these two, first two nodes and mark the smaller as head and tail both. And whichever you marked as head and tail, you move ahead in this linked list. Now remaining steps are simple. What we are going to do now is we are going to compare A and B and whichever is smaller, we are going to add it after the tail. Adding after the tail is really simple. We just need to make the tail.next equal to A or tail.next equal to B, right? So which of these two is smaller? 10. So we are going to simply make tails next equal to 10. That's the change we are going to do. And we are going to move ahead in the linked list because we picked the node from this linked list, right? We are going to move ahead in this. And we are going to mark this as new tail also. So this is our new tail. So these are the changes we make after the first iteration, right? We picked the smaller of these two. We moved ahead in the linked list because we picked from this linked list. So we move ahead in this linked list and we mark it as tail. Now we again compare A and B. And which of these two is smaller? B is smaller. So what are we going to do? We are going to make tails next as current B. So we are going to change this link and we are going to make tails next as B. And we are going to change tail also. So tail is going to have reference or pointer to this node now. And since we have picked a node from this linked list, we are going to move ahead in this linked list. So B is going to come here. Now we again compare A and B. And which one is smaller this time? B is again smaller. So we are going to change tail again. And before we change the tail, we are going to make tail arrow next or tail dot next equal to B, which is already same. So it's going to overwrite the same value. And we are going to mark this as tail. And we are going to move ahead in this linked list. So B is going to be here. So this is the change we do after the next iteration. We again compare A and B. And again, B is smaller. So what are we going to do? We are going to move ahead in this linked list. We are going to move ahead our tail, right? We are mainly going to overwrite this next, right? And B is here now. And now what we do is we compare A and B again. And this time A is smaller. So what are we going to do? We are going to make A as tails next and we are going to move ahead in this linked list. This 20. So 20 is smaller than 35. So we pick this node, we make it tails next. So we break this link and we make it tails next. And we move ahead in this linked list. We come here. Now we update the tail. Right, we update the tail to this node. So tail is here now. And once we update the tail, we are going to compare A and B again. And which of these two is smaller? 30 is smaller. So we are going to make it as tails next. So tails next is going to be 30. It's already tails next. So it's going to overwrite the same value. And tail is now going to come here. Tail is now going to come here and A is now going to come here. And we are again going to compare A and B. So which of these two is smaller? 35 is smaller. So we are going to make this as tails next. And we are going to update the tail. Tail is here. And we are going to update the B also to this next. So B is now going to become null. And if any of these two linked list references or pointers become null, we stop this loop. And once you stop this loop, whatever is remaining in the other linked list, you simply attach it at the end of tail. So this is going to become now tail next. Suppose there were more nodes like 50, 60, 70, they will also become tails next. We simply attach this part of the linked list to this tails end. So 35 next now become 40. And this is how we got the merged linked list. Now please pause this video and try to write down a function that takes two linked lists as arguments and returns the merged linked list as a return value. Let us talk about the detailed implementation. Here is C++ code this side and this side we have Java code. What we do in both the codes, first thing we do is we check for the corner cases. If any of the linked list is empty, we simply return the other linked list. So these two lines are to handle the corner cases. After we have seen that both the linked lists are not empty, they have something in them, we try to merge them. And in order to merge them, we need to maintain tail pointer in C++ and tail reference in Java. So we initialize our tail as a smaller of 2. If A's data is smaller, then we initialize our tail as A. If B's data is smaller, then we initialize our tail as B. And whichever is smaller, we move ahead by one position in that particular linked list. We also need to have head of our resultant linked list. And this head has to be updated only once. Tail we are going to update in this loop, but head is going to be updated only once because head has to be known so that we can return the head at the end. So we initialize our head and tail in this part. And then the next part is actual merging part that we talked about. We run a loop while any of the linked lists does not become empty, right? While both have some data, we keep on traversing both. We keep on picking the smaller of the current two nodes. If A is smaller, if A's data is smaller, we make tail next as A, then we make tail as A, then we move ahead in that linked list. If B's data is smaller, then we make tail next as B, we make tail as B, and then we move ahead in that B linked list. And if any of these two linked lists become empty, then we come out of this loop and whatever linked list has extra nodes, we append that linked list at the end of the tail. If A is null, if A does not have any extra nodes, then we append B at the end of tail. Else we append A at the end of tail. So that's the simple idea we follow in this implementation. Let's now do a dry run for this example linked list. So we begin our execution from this line. A is not null, B is not null, so we do not fall here. Now we check if hat's data, if A's data is smaller than or equal to B's data. It is not, right? B's data is smaller. So we come to the else part. When we come to the else part, we mark this as head, we mark this as tail. And we move ahead in this linked list. So initially our A's and B's were here at this point. Now since B is smaller, we move ahead in this linked list. So our B now comes here, right? And now we begin our main loop. So this extra thing is done to make sure that we have the correct head, and tail is also pointing to or referring to a valid node so that we can update tails next inside the loop. That's the reason we have these extra conditions, extra thing outside this while loop. Now we enter into the while loop, and inside the while loop we have simple logic. We compare A and B's data, and A's data is smaller. So what are we going to do? We are going to make tail.next equal to A, which means we are going to break this link and we are going to make it next of this node. And after that, we are going to make tail equal to A. So our tail is now going to move from here to here. So tail is now going to become this node. And after that, we make A equal to A.next or A arrow next in C++. So A now comes here. That's what happens after one iteration of this loop. And in the next iteration, we again compare A and B. And this time A is smaller. So this time again A is smaller, right? So what are we going to do? We are going to make tail.next equal to A. So tail.next is anyways A and is going to be overwritten. And after doing this, we make tail equal to A. So tail now moves from here to here. This is now tail. And after updating the tail, we make A equal to A.next. So A comes here. Right? And now we begin the next iteration of this loop. In the next iteration, we again compare A's data and B's data. And A's data is again smaller. So what are we going to do? We are going to again make tail.next equal to A or tail arrow next equal to A, which overwrites the same pointer, right? Pointer reference. So we again have tail.next equal to A. So tail.next was already A. Now after that, we make tail equal to A. So tail is now going to become A. So this is now new tail. And after that, we do A equal to A.next or A arrow next, and A becomes null now. Right? And now we begin the next iteration from here, and next iteration does not happen because A has become null now. So we come out of the loop, and when we come out of the loop, we check if A is null. Yes, A is null. So what are we going to do? We are going to make tail.next equal to B, which means we are going to make tail.next equal to this node. That's all. And you can see that both the sorted linked lists have merged. Let us now talk about time complexity of this simple merge process. If m is the length of first list, n is the length of second list, then it's going to need big O of m plus n time. We are using big O, not theta, because consider the situation when one linked list is empty. If one linked list is empty, then it's going to simply need theta one time, right? Because you will simply return the other linked list. So that's why we are using big O notation. The upper bound is big O of m plus n. Because what will happen in the worst case, your both linked lists have half nodes and they are mingled, the items are mingled with each other really well. First list is like 5, 15, 25 and the second list is 10, 20, 30. In this case, it's going to traverse both the list till end and then it's going to return the result like what happened in this earlier example we discussed. So in worst case, it's theta m plus n, but in general, we can say the time complexity is big O of m plus n. Auxiliary space required for linked list merge is big O of 1, and this is where it is better than arrays. In case of arrays, we generally need extra space to merge two arrays. This extra space is not required in linked list because in linked list we can insert items in the middle and we can remove items from the middle in big O of 1 time.